Hello, this is the Section 3-4 lesson. For this lesson you're going to need your calculator. In last section we saw what we call the range rule of thumb, which said that 95% or a vast majority of all our data values lie within 2 standard deviations of the mean. And from that we can calculate a usual minimum value and a usual maximum value. We say that usual values are within 2 standard deviations of the mean. Let's look at a couple of examples of using that range rule of thumb. So the mean of electrical consumption amount for the author's home during a 2-month period is 2,838 kilowatt hours and a standard deviation of 504 kilowatt hours. For one particular 2-month period, the power company recorded a consumption of 578 kilowatt hours. Is that amount unusual? Well, we can use the range rule of thumb to answer that question. And we're going to look at this maybe a little bit different than we did in the previous section. So in this set of data we have a mean of 2838, standard deviation of 504, and we have an x value of 578. So let's look at the distance that this x value is from the mean. So x minus x bar, we do that arithmetic, it's a negative 2260. Negative means that this x value is below the mean. Well, notice that this is more than 2 standard deviations away from the mean. 2 times the standard deviation is 1008, so this data value is more than 2 standard deviations away from the mean. One use of standard deviation is that we use it as a unit of distance, particularly from the mean, as we do in this case. So we're more than 2 standard deviations from the mean, so it is unusual. Now our next example is a similar type situation. Aluminum cans have a thickness of 0.0111 inches, have an axial load with a mean of 281.8 pounds and a standard deviation of 27.8 pounds. So axial load, that's like the amount of force that it takes to crush a can with this thickness. One particular can had an axial load of 504 pounds. Is that unusual? So similar question, we're going to answer it in a similar way. Here we have a mean of 281, a standard deviation of 27.8, and our x value is 504. Let's look at the distance from the mean, x minus x bar. That comes out to be 222.2. So it's positive, so that means we're 222 units above the mean. Well, if we take 2 times the standard deviation, that comes out to be 55.6. So 222 is obviously more than 2 standard deviations, and so again we are more than 2 standard deviations away from the mean, and so this x value of 504 is unusual in this context. Okay. So now here we're going to compare these two, kind of like what we did in the last example from the previous section. Which of these data values is more unusual in the context of the problem? In the first one we were 2,260 units below the mean, and the second one we were 222 units above the mean. Well, we might be tempted to say that the first one is more unusual because it's further from the mean. However, notice in that first example we're using larger numbers. Our mean is a lot larger than in the second example. So we need to be careful about comparing those distances. We need to put things into context. We're going to put these differences in context similar to what we did with the coefficient of variation from the previous section. Okay. And so the way we're going to put differences in context is to define what we call a z-score. Z-score is something we'll be using quite frequently starting in chapter 7. Here we're going to define it for the first time. So a z-score of a given value x is the number of standard deviations x is from the mean. So here's the formula. Z is x minus x bar divided by s. X minus x bar is the distance from the mean divided by s to get the number of standard deviations it is from the mean. Now one important thing about z-scores is that they have no units. They are unitless, so that means we can compare z-scores from 2 different sets of data. Okay, so in the first one, we see our numbers there in the first example. X is 578, subtract the mean of 2838, divide by the standard deviation of 504, and you see the calculator command there. Notice again that we put that subtraction in parentheses, because if we don't, the calculator will not do order of operations properly. So this x value has a z-score of negative 4.48. That means we are 4.48 standard deviations below the mean. In the second example, we have an x value of 504, subtract the mean of 281.8, divided by the standard deviation of 27.8, and we have a z-score of positive 7.99. That means we are about 8 standard deviations above the mean. So now we can compare these z-scores to determine which is more unusual. Larger z-score means that it's more unusual in the context. And so we would have to conclude that x value of 504 in that second example is more unusual than the x value of 578 in the first example. Now, using this idea of z-scores, we can restate our range rule of thumb, which says that ordinary values are within 2 standard deviations of the mean. 2 standard deviations of the mean means that they have a z-score between a -2 and a +2. So here you see a little graph that illustrates the range rule of thumb in terms of z-scores. If the z-score is between -2 and +2, it's an ordinary value. If it's less than a -2 or greater than a +2, then it's considered unusual. Next, we need to define a concept that you're maybe somewhat familiar with. It's the idea of a percentile. And a data value x is the 80th percentile of a set of data, denoted by p sub 80, if 80% of the values in the sample are less than x. Now, there's nothing magical about the number 80. We could change that to any number between 1 and 99. So we could talk about the 5th percentile, the 75th percentile, the 99th percentile, or anything in between. Okay? So as an example, my son Martin, his weight at 12 months was about 25 pounds. The doctor said that means he's at the 90th percentile. 25 pounds is the 90th percentile of the weights of all 12-month-olds. What that means is that Martin is heavier than about 90% of kids at his age. My mom is a nurse, and she said that she would explain this to people by saying, if I had 100 one-year-olds and lined them up from the lightest to the heaviest, Martin would be the 90th kid in line. He's heavier than about 90% of those kids. So as an example of calculating percentiles, we're going to look at this set of data, which is the ages of the 76 actresses that have won the Best Actress Award at the Academy Awards. And they range from an age of 21 up to an age of 80. Okay. We want to find the percentile corresponding to an age of 50. So age of 50, that is a particular data value. We want to find the percentile that corresponds to that. So to find a percentile of a given value x, here x is 80 in this case, we need to count the number of values that are less than x, divide it by the total number of values, and then take it times 100. We multiply it by 100 to turn it into a whole number. So looking back at our table, we see that the age of 50 occurs in the bottom left-hand corner. And so we need to count the number of values less than 50. Well, we could do that, or another way to do is count the number of values that are greater than or equal to 50 and subtract that from 76. So we have 1, 2, 3, 4, 5, 6, 7 values greater than or equal to 50. Subtract that from 76 and we get 69 values that are less than 50. So my percentile of value x is 69 divided by the total number, which is 76. Take that times 100 and I get 91. So we would say that the value of 50 is at the 91st percentile. That means that roughly 91% of my data values are less than 50. Okay, so we just defined percentiles and described how to calculate them. There are a few percentiles that are given special names. The first one is the 25th percentile, p sub 25, and it is given the name the first quartile and denoted by Q1. So the 25th percentile would be a data value for which 25% of our data values are less than. the 50th percentile P50 is called the second quartile and denoted by Q2. 50th percentile is the one that's right in the middle. 50% of the data values are less than it, 50% are greater than it, and so the 50th percentile is the same as the median. The third one is P sub 75. The 75th percentile is called the third quartile, it's denoted Q3. That is a data value. 75% of the data values are less than that particular data value, and 25% are greater than it. Okay. Then with a set of data we have what we call the 5-number summary, which consists of our minimum value, our first quartile, our median, which is the same as the second quartile, the third quartile, and then the maximum. These are 5 numbers that summarize the overall set of data. And then associated with a 5-number summary is what we call box plot, which is a graphical description of the 5-number summary. So let's look at some sets of data, and we'll calculate 5-number summaries and do box plots. So here we have the weights of several different types of pennies. We have wheat pennies, pre-83 pennies, and post-83 pennies. And we want to compare these 3 sets of data. So look at the wheat pennies and the pre-83 pennies. We see that they all weigh around 3 ounces or so, whereas the post-83 pennies all weigh around 2.5. So looking at the numbers, we see that the wheat and the pre-83 pennies are roughly the same weights. The post-83 pennies tend to be a little bit smaller. And we want a graphical description that illustrates that. And so first thing, we're going to calculate the 5-number summary for the wheat pennies. So if you want to enter that wheat penny data into list L1 on your calculator, again you can do that by going to Stat, Edit, enter that data into L1. Then once you've got it calculated, hit Stat, Calc, and 1 variable statistics. That's going to calculate a 1 variable statistics for that set of data. Hit enter twice. If you scroll all the way down, you see our 5-number summary. The minimum, first quartile, median, third quartile, and the max. So there's those 5 numbers constitute our 5-number summary. Now in our box plot, we're going to graphically describe that 5-number summary. So to do a box plot on our calculator, select Stat Plot, which is again above the Y equal key. Select the first plot, A, and then format the window so it looks like this. First of all, make sure it's turned on. Select the second type there in the second row. That's going to be our box plot. The X list is the list that contains the data. Select L1. For frequency, choose 1. And now to graph it, hit Zoom and then choose option 9, Zoom Stat. When you do that, you should get a graph that looks something like this. This graph is our box plot. Here are the weights of our pennies are on the horizontal axis. The vertical axis has no real meaning. The left hand of this box plot is our minimum value. Now there is no, our axes aren't labeled here, so these are a little bit hard to read, but that left corresponds to the minimum value. That first long line on the left, it corresponds to our first quartile. That middle line, vertical line, is our second quartile or median. The line right next to that is the third quartile, and then the short line there on the right corresponds to the maximum value. And from this we can see a little bit about how spread out our data is. That line on that horizontal line on the left corresponds to a range of 25% of our data values. 25% of our data values are between the minimum and the first quartile. There between the first quartile and the second quartile we have another 25% of our data values. So we see that those 25% of the data values aren't quite as spread out as the first 25% of our data values. Between Q2 and Q3 we have another 25% of our data values. Again, those are not as spread out as the first or the second 25%. And then from Q3 up to the max we have our last 25% of our data values, and we see that that's fairly spread out. And so we get an idea of how spread out the data is. It's also a graphical description of our 5-number summary. Box plots are also called box and whisker plots. Okay. Now one use of box plots is that it allows us to compare sets of data. So if you enter your pre-83 penny data into list L2, select stat plot, and then plot 2, you can format your window so it looks like this. So we're going to set up another plot to do another box plot, and format it so it looks like this. Make sure you enter X list as L2, and then select zoom and option 9 zoom stat, and your window should look like this. We have two box plots. The top one corresponds to our wheat penny data that we already saw. The second one corresponds to the pre-83 penny data. Now again, box plots are useful for comparing data. What we see here is that first of all, those two box plots kind of overlap, and we see that the minimum value for the pre-83 pennies is a little bit larger than the minimum value for the wheat pennies. The maximum pre-83 penny data is a little bit smaller than the maximum value for the wheat pennies. We see that the first quartile for the pre-83 pennies is a little bit less than the first quartile for the wheat pennies, so on and so forth. But the fact that those two graphs aren't terribly different is an indication that those two sets of data aren't terribly different either. Okay. So based off comparing these two box plots, we'd have to conclude that there isn't much difference between the two sets of data. They're obviously not identical, but there isn't a great deal of difference. Now we could do the same thing. We could enter the post-83 penny data in list L3, set up a third statistical plot, and graph all three, and we see that that box plot for the post-83 pennies is quite a bit different than the box plots for either of the other two sets. So we would have to conclude that the post-83 penny data is significantly different from the other sets of data. In fact, those values tend to be quite a bit smaller, which again we saw from the data just looking at the raw numbers, but a picture is easier to look at than a set of numbers. So that's it for Section 3.4. The Course Compass homework is titled Section 3.4.